So these lectures are basically on this idea that there could have been some black holes formed in the early universe. Why do we want that? So what we know for certain is that a lot of the stuff that is circulating in the universe, we don't know what it is, right? So one is dark energy and the other one is dark matter. Now, the idea is that, well, the dark matter, so dark energy, I still don't know what it is. So we'll find at some point. But for dark matter, what we know is that all this matter that is around is basically only interacts gravitationally. And if interacts between these particles, is very weakly interacting, okay? So let's take this thing from the bottom point, and let's say that this is just interacting gravitationally. So the most natural object that interacts gravitationally is a black hole, okay? So if I have small black holes that circulates around, then these black holes only interact gravitationally, and then they can fully be what we call as dark matter. Okay, because they do not emit any light, so they're dark, as dark as they can be, okay, and they only interact gravitationally. Now, of course, you tell me, well, but we actually kind of observe black holes, okay, so we know more or less how many black holes are around. Well, if we, actually, Zriran showed us in the last part of the lecture some constraint on these black holes. So if I take the fraction of black holes that could be of dark matter, so if this is 1, is the full of dark matter, this is less, is some part of it. So we find that there is, so if this is 1, of course, you could go back to the slides to see a better plot than my drawing, but more or less this is the thing. So there is a line here, which I explained, then there are other lines there, okay, and those are the constraints. So primordial black holes that could be of dark matter are in the region that is not shaded. Now, what do we observe? How do we observe this thing? So first of all, this thing is for large black holes. So this is, in terms of solar masses, okay, in terms of solar masses, this is roughly, and this is continuously changing, okay, 10 to the minus 16 solar masses, and there is a hole here of 10 to the minus 12. These constraints here are the black holes that we see, because if there is a black hole, there is gravitational lensing, for example. Okay, so we are gonna see, for example, multiple image or macro lensing. You probably have seen all these things, okay? So we can count those objects, and we can say that, well, those are not enough to cover all we need for dark matter. In this case, instead, the black holes are very small. And if the black holes are very small, we heard about Hawking evaporation. So if a black hole is extremely small and was born in the past, then would be evaporated by now. So we cannot use it for dark matter, okay? And even if it didn't evaporate until now, it emitted so much energy density in terms of radiation that would change completely the BBN nucleosynthesis constraints. Okay, so those are ruled out. So the only window we have for dark matter to be in form of black hole are black holes of asteroid mass, basically. Okay. Now, as your national hero, which is Chandrasekhar, will tell you, it's impossible to form a black hole astrophysically of mass like an asteroid. It has to be at least solar mass. Okay. Of course, we can have other black holes here, but they are not the full of dark matter. For example, in the case of LIGO, we could have very large black hole, but they are not just the whole mass that we need for the dark matter. Okay. So, as Chandrasekhar would prove, then we cannot actually form astrophysically those black holes. Okay? So those black holes should be formed in another way. Okay? So they have to be formed after structure formation, before structure formation and before the stars formation. Okay? So for this reason, they are called primordial black hole, because they are before the formation of structure. Okay. So the idea is well, these 3 lectures that I will do, I will try to show you how to actually form those black holes during the evolution of the universe, and to count them. So to know how many statistically there would be in the universe, to see whether they could be the dark matter. Okay, so that's the idea. Okay, so I'll use this plot, and I'll start with the full thing. So the first thing that you always hear from people is the following thing: a large overdensity collapses into a black hole. Okay, so you hear this. However, this is as imprecise as it could be. Okay, so we have to be more careful when we say this sentence. Okay, so the first part we will actually be careful on understanding what it means that something collapses into a black hole. Okay, because for example, let me give you an example. I am a large overdensity here. Do you see? I mean, the background is flat, so I am a very large overdensity. Do you think I'm a black hole? No, right? So that means that actually large overdensity, even if they are super large, non-perturbatively large, like me, they will not form a black hole generically. Okay? So we have to be very careful about this statement. Okay, so first of all, then let's anyway define what we mean for energy density. So let me suppose that I have a fluid, okay? And this fluid has a word line, which we define by a 4-vector, u mu, okay? So this fluid will have also an energy momentum tensor that you have seen all along the courses, okay? And the energy density we define is simply the contraction of the energy momentum tensor with this word line, okay? The way, so I will use all the way units g equal to h bar equal to c equal to 1. Okay? So the Newton constant equal to 1. And the way I write this energy density forms actually a scalar. So it means it's a coordinate invariant. Okay? Because I define a fluid line and then I'm contracting with energy momentum tensor. So if I change coordinate, this object is the same. It's not going to change. Okay? However, now let me suppose the following thing. Let me suppose, because what we are thinking is black hole that is formed in a universe that is expanding. So the universe itself has an energy density, okay, because it's expanding. And the idea that we have in mind is that some large overdensity will pop up here and there, and under certain condition will form a black hole. So what we can think is that, okay, there is an overdensity that is the average overdensity, which we say is, this is a Friedmann-Robertson-Walker universe that is expanding. Now, by now, you know what is a Friedmann-Robertson-Walker universe. And this is the energy density that is completely homogeneous. Now, what I can do, I can rewrite my new energy density. So let me suppose I have locally some inhomogeneous energy density. So this will be rho. Well, this rho I can write in terms of rho bar plus delta rho. This doesn't necessarily need to be small. It's just that I'm taking out the homogeneous part, okay, that goes to infinity, like homogeneous, and then something that locally is inhomogeneous, okay? Now, what happens also is that not only the energy density is changed, but as well the velocity, the word line of the fluid will change. Okay, because if I modify the fluid, then also its word line is changing. Okay, so this u mu. Now let's suppose that I take coordinates that are attached to this word line, to this homogeneous word line, which is the cosmic time. Okay, so this is simply equal to -1 plus some perturbation all in the zero component and in the vector component. Okay, so the word line will change as well. So that means that now my scalar that was rho equal to t mu nu delta u mu, delta, well, sorry, u mu, u nu, we'll have, well, the part that is T bar 0, 0, which is the background energy density. And then, of course, we'll have, let me call it some delta T0, 0, T, well, delta rho, which is nothing else than multiplying the delta T with the delta U. Okay, so we can write down, of course, delta T 0, 0 multiplied by delta U 0 square and all these other terms. Okay, so then what I can do, I can define, well, delta rho, so this is simply rho bar. So delta rho that we have in this bold statement that large over density collapse into a black hole, it's simply equal to rho minus rho bar. But now, this is no longer a scalar. Okay? Do you see that? Why? Because I can always choose coordinate such that this delta rho, so this part, that is the product of, so it's basically those terms, delta T0, 0 plus 2 times T bar 0 mu delta U mu plus delta Tij. This is a scalar. Well, this is one component. This is all contracted. So I always have gauge freedom. I always have the freedom to choose coordinates such that this guy is equal to 0. Okay? So depending on the coordinate I'm using, the overdensity, what we call a overdensity, could be 0. Okay? So we immediately see that talking about overdensity for at least when we have a background, it's meaningless. Okay, is that clear so far? Because we always use gauges in which the overdensity is equal to 0. So does that mean that if I have an overdensity in certain coordinate that is large, black holes do not form? So the opposite of what we were saying before. No, it doesn't mean so. So then let's see how we really understand black hole formation. Okay. So the first thing that I will do, I will actually go back to something that you probably will see in the next lecture, which is gravitational collapse in flat space. Let me give you an overview of what is going on there. So probably we will go more in details there and you will understand even better. But let me give you some overview of what is going on. So let me suppose then that I have actually asymptotically flat space-time, okay? And I have a collapse of something, okay? Or of a ball of something. So that means that in that case, rho bar is equal to 0. Okay? I don't have mean value for the overdensity because all is overdensity. So that means that actually this delta rho coincides with rho, right? And so, because this is the whole energy density, so this delta rho was basically the part that is inhomogeneous, and here is all inhomogeneous. Okay, so in this case, actually rho is a scalar. Okay, so this is either 0 or non-zero. Okay, in that case, so in asymptotically flat.
Did you say we have a background which is flat space-time?
We have flat space-time, so we have Minkowski at infinity. Okay, so I'm going to the case in which it's not the formation of black hole in a universe expansion, but it's just in a flat space. Okay, just to understand what is going on. So let's think now in a Newtonian way, because always is easier to understand things in Newtonian way. Okay? We always understand better. So we can think of that the collapse of an object is such, it happens whenever the gravitational potential is larger than the pressure that is in this object. Because the pressure will try to make things exploding. Think an atomic bomb. Okay? But the gravitational force is always attracting. So it's always a fight between the two things. So what we need to have is the gravitational potential to be large enough for this object to actually contract instead of expand because of pressure. Okay. Now, again, from our Newtonian interpretation you did probably many years ago, but you will probably remember. You remember the Gauss law, right? The Gauss law tells us that the strength of the gravitational potential, which is the flux, depends on a surface, on an enclosed surface. Okay? It's very important that it's a surface, not a volume. Okay? So really, so if you go in Gauss law, so you find that the gravitational potential is proportional to the flux on a surface. Okay, so we have an enclosed surface, whatever it is, and we calculate the flux across this surface. Okay? So you remember that the gravitational potential is roughly the integral of, the flux is roughly the integral of the gravitational potential multiplied by the surface area. Right? This is the Gauss law. Okay? So, so if you consider now, let's consider a sphere. Okay? Let's imagine everything is spherically symmetric around the center for a second, and let's consider a sphere. Okay? Now, in flat space, the funny thing, or not the funny thing, is that the volume of a sphere and the surface of a sphere are related by the radius. Right? This sounds like a trivial thing, but it's not in general relativity. So in flat space, what we have is that, 4 pi divided by 3 r to the cube is the volume, right? While 4 pi r squared is the surface. So they're obviously related, right? I mean, that's given the radius, it's just the angle that relates the two. Okay? However, what happens in general relativity? In general relativity, they might be not related. So the volume and the surface may be two different things. Okay? May depend on two completely different functions. That's very important. So let's see. Okay. So suppose let me check only the special part of a metric. And this is spherically symmetric. So if it is spherically symmetric, you take your favorite book, like Landau-Lifshitz, and you check that you can always find the coordinate to write this thing in diagonal form. Okay? So the special part is going to be dl squared equal to some function that we call it grr r dr squared plus, let me call it with a big R, the omega squared. Okay? So this is explicitly the spherical symmetry because I'm choosing angles. Okay? And this is what is called the areal radius, okay? Which is a function of R. Now what happens is that the volume in this case is, of course, 4 pi, the integral of square root of grr r squared dr. Right? Because it's the trimetric, so the trimetric is simply the determinant of this guy, okay? And then integrated over R, okay? While the surface, it's still 4 pi r squared. Okay? So you immediately see that the two objects might be completely unrelated. Okay?
So this GRR and R of R is induced by the presence of delta rho. Is that what we are?
Yes, correct. So for now, it's just take a generic metric, and of course, given a certain rho, you will get some metric which is spherically symmetric. So let's assume that it's centrally peaked. We'll talk why this should be so, but let's simplify the problem. And there is a center. It's going down at infinity. It's all smooth. But then, of course, we'll generate a metric that generically has this form. So generically, the volume and the surface will be two different objects. Okay, maybe completely unrelated. So, so then let's think again the Gauss theorem. So the Gauss theorem is telling us that actually the gravitational potential depends on the surface. Okay? In fact, the Gauss theorem will tell you that depends on the mass enclosed in this surface. So somehow, to make a connection to that, we have to think about a kind of a fictitious volume that is determined by an enclosed surface. Okay? So if I take a sphere, then the most natural way to define actually a mass enclosed in this surface, so to think about the surface, is by using this function here, which is the area radius, because this is what determines actually the surface, okay? Not to use the full volume, because this would be another object. So what we define is a new volume let's call it with inverted comma, okay, which is basically, so the volume is going to be 4 pi integral of r squared r prime dr. So this will be basically the volume of the sphere by using the area radius, so what it determines the enclosed surface. If this is the volume, what I define, I'm going to define a mass, okay, which is nothing else than the integral of the energy density enclosed in this volume. Okay, so
R prime is dr by dr.
correct. Sorry. Yeah, in this case we have only r because I'm taking static case. Okay. So let me define the mass as equal to 4 pi, the integral of the energy density, but now this energy density, it's 0 at infinity, so we are not on an expanding universe, we will go there, but now we are doing the example on flat space, okay? On asymptotically flat space. So it will be integral rho r squared r prime dr from, of course, 0 to r, which is the coordinate radius of the sphere. Okay? So we define this mass. As you can see, this mass is different from the mass that you would think. I mean, I insist on this, because if you would think about a naive mass, then what would you do? You would do the integral rho on the volume. But the volume gets also the GRR, okay? But the mass that we need actually for the gravitational potential, as I said, is related to the Gauss law. So it's related actually to the surface, okay? This mass, it's called Misner-Sharp mass. Actually, it's generalization that we're gonna do in a second. Okay. Okay, so now, so far, what we have done is the case of a static space-time. Okay, so let's do a little generalization of this. So now let's suppose that instead of being a static space-time, it's kind of a dynamical. So this energy density is still asymptotically flat, okay, but this energy density is evolving in time. Okay, so that means that everything here will also depend on time. Again, you can go in your favorite book, which mine is, again, Landau-Lifshitz, and you can find that, again, you can write your metric in diagonal form, if it is spherically symmetric. Okay? This is just a gauge choice. So, and now I want to use the same concept, but this time, I'm thinking the following, that at each time, so if I make a picture of the system at a given time, then the potential energy is basically what I calculated there at fixed time. So each time I will have a new potential energy, okay, gravitational potential. So that means that basically, although now everything depends on time, so let me erase this, and then I just plug, I just put a t here and a t there. Okay, so now everything depends on time. However, what I still define as a mass, which now is the Misner-Sharp mass, the original definition, is the following, that this is still 4 pi integral of the same thing from 0 to r rho r square r prime dr at a given dt equal to 0. So each time I have a different, so it's a fixed time, okay? Yeah? You see, wait,
something
let,
like Birkhoff's theorem or something or two.
yes.
The metric outside will.
The metric outside will be Schwarzschild, for sure. Yes, the metric outside will be sure.
Only inside.
I'm talking about inside. I'm talking about the definition of the mass. So I'm integrating over inside. You can see that here, in fact, you understand that this is the volume of a sphere, because if I have only prime here, this is simply dr. So I'm simply calculating r squared dr. Right? So this is what I was doing before, r squared dr, which is the volume related to the surface of a sphere. What I'm doing here, if you want, I'm still doing r squared dr, but a fixed dt. So when I do this derivative, I'm not taking the time derivative of dr. Okay. So at each time, I will have, in principle, a new mass. So a new potential, gravitational potential. Okay? Yeah? More or less? You have doubts? No. Okay, good. I never know, because you guys do this when you also agree, but then I don't understand when is the other way around. So in your case, it was yes, or it was yes. Okay. It would be function of time in general, right? So that's why the gravitational potential in general here would be function of time. So what I'm saying is that at each time we calculate the new mass. Okay. Okay. So this is the mass. This is the mass that I will use. Okay. This definition, it's kind of a natural definition from Gauss' law in Newtonian physics. Okay. Salute. Okay. So now let's see something. So let's see how a black hole is formed then. Okay, so I define a mass, but so far I didn't tell you how the black hole will be formed. Okay, so in the 70s, there was this conjecture by Thorne, which is called the Hooke conjecture. Okay, so the Hooke conjecture is simply telling us that a given mass enclosed in a hoop. You know what is a hoop, no? So it's like this hula hoop, no, that we do when we are small. Okay, so if we are enclosed in a hoop of radius, so if I have a mass that is enclosed in a radius r, which is equal to 2 times the mass. Okay, so it's very naive if you want this conjecture, but it actually turned out to work. So if you have a mass that is enclosed on a hoop, which is 2 times the mass itself, you recognize this as the Schwarzschild radius, then this object will collapse. Now, why is not this Schwarzschild radius? Because of course this is not a Cauchy horizon, because everything is dynamical in time, but it's what is called an apparent horizon. Okay, an apparent horizon is a sphere where whatever is inside has to collapse. Okay, but still you can get stuff. Okay. Okay, so then, but you see in this conjecture, it actually works pretty well in all numerical code, whatever. So if you check and you have a spherically symmetric object, in fact, not only for spherically symmetric object, for any symmetry so far it works. Okay, so if you have a mass which is enclosed in this hoop, this will form a black hole. Okay, so this is tested in millions of codes and everything. Okay, but we see that again we have this word hoop. Now the hoop, it's related to the surface again. The hoop is not a volume. The hoop is a perimeter. Okay, so again we see that this mass that Thorne is talking about is again related to the mass, to the Newtonian mass associated to the flux of our gravitational potential on a closed surface. Okay?
So the mass has to be inside this,
The hoop, yes.
but any part of the hoop, that's all. I mean,
Well,
like
what you have to have is that this hoop, so if you take it around, this hoop, it has to enclose all the mass. So you have you have whatever,
a long ellipse.
so you take this guy and then you move it around. There. And your mass has to be always inside in all possible directions.
Why aren't we saying a volume and talking about a hoop?
Precisely because the gravitational potential is related to the surface. That's kind of my understanding on why we talk about the hoop. And we are not talking about, if you want, the area inside. Because we could have talked about the area inside and moving the area all around. But because the area and the perimeter are different in general relativity, we have to decide what we are talking about. And in fact, it turns out to be because, if you want, the trapped surface are not trapped volumes, if you want. Okay? So what is important is the surface, always. Okay?
Is this like a two-sphere that he's calling a hoop?
Sorry?
Two-sphere calling a hoop?
No. It's a hoop. I mean, a hoop is a ring. Yes, is a ring. Ring. You know what is a ring? You know? Yes. So it's a ring that you take it around all your object. Okay? And so your object has to be inside this ring. So if the object is inside this ring, it's going to collapse into a black hole. Then we have to give a meaning of this R and this M, because this is a very naive way of saying, well, if something is smaller than R, so yeah, but what is R in general relativity? Okay? And now we know what it is, because this R, if at least in spherical symmetry, this R is exactly the areal radius, because it's the part that describes the surface, the area of the surface. So this R is this. Okay, when we write in spherical coordinate, it will be the part that multiplies our sphere. Okay? And what is the mass? Then the mass is the one associated, again, to the surface. So it's what is called the Misner-Sharp mass. So now we have a meaning of this hoop conjecture, even in the case in which everything is time dependent, which is whenever this function that let me call compaction function, which is 2m divided by r, so this is called compaction function. Well, not yet, let me not call it yet, because it will be something like this. So whenever this guy is of order 1, then my object is collapsing into a black hole. Okay? So this is for asymptotically flat. Okay? And everything now, so let's go back to the gauge problem we had before. You remember I told you that, well, we have to be sure that if we change the gauge, then we are not making to 0 something that is not 0. Okay? So we have to make sure that this is physical. Well, what happens is that in spherical symmetry, so let me stick with spherical symmetry, this function here, the area radius, which is the radius of a sphere in spherical symmetry, is actually a scalar. Okay? So if you want to calculate in different coordinates the radius of a sphere, you will find always the same number. Okay? This you can prove that R is a scalar. And as we said, the energy density in asymptotically flat is a scalar. Okay? So this object, it's a scalar, and so this object divided by the radius, which is again a scalar, is again a scalar. Okay? So this is a completely physical condition to form a black hole. Okay? So if I change coordinate, it will look like different, but the number will be the same. Okay?
So R is that function. Is that correct?
R is this function here that multiply the angular part.
And that's a scalar.
That's a scalar. In spherical symmetry, it's a scalar. Yes. The reason is you can imagine that in spherical symmetry you have symmetries, which are the rotation. So all the function that multiply this rotational symmetry it must be always the same, because otherwise you have to change also the angles. Okay? So in spherical symmetry, this is a scalar. So this function, which is called the area radius, it is a scalar. Okay? And define the surface of a sphere and the perimeter as well.
But since it's a component of a metric,
I know it's a component of a metric, but as you know, for example, in perturbation theory, so you have some term in component of a metric that given in a gauge are scalar, meaning that
but
if you
they are
change,
scalar under, different, not general coordinate transformations. They are
in this case is yes, in this case is a general coordinate transformation. So what happens is that if you change the coordinates, the metric will look like different. Okay, but if you calculate the surface of a sphere in spherical symmetry, so you change coordinate, you go to Cartesian, I don't know, whatever. Okay, still the surface will be related to this angle, this solid angle multiplied by the same number. So that means that although the metric will change, the function that determine the radius, it's a scalar. Now, of course, in certain coordinate, which is those coordinate that makes the metric diagonal, it's explicit. Okay, so these is the explicit form of this scalar that we call radius of a sphere. Okay, is that clear? For of course, you can change coordinate and get other function, and then you will have some sum of different component of the metric, whatever. Okay, so so far so good. So then I could define a mass that is a complete scalar for spherical symmetry. Okay, and I could define a condition that is a scalar, so is an observable. So this condition, when this is equal to 1, will form a trapped horizon, and then your object will collapse into a black hole. Okay, so this is for asymptotically flat space. You'll probably see these in all different forms from the next lecture, because I think the next lecture is on gravitational collapse, no? Or
that's from tomorrow.
yeah, from tomorrow lecture you will see also this in more precise way, but this is more or less the story. Okay. Okay, so now, in fact, actually, I can give you also a reference if you are really curious. If you are really curious on these things of the fact that R is actually a scalar and formation of trap horizon, it's a beautiful paper, which is GRQC 94. It's very mathematical, but 002, and is of high work. Okay, so if you are curious to expand a little bit this thing, you can simply check that. Okay. Okay. So now, so far so good. This is asymptotically flat. However, the idea we have now for primordial black holes, how are we going with time? Yeah. The idea we have now for primordial black holes is that we are in a universe that is expanding. So definitely it's not asymptotically flat, but it's asymptotically expanding universe. Okay. And the idea we also have is that we will have some overdensities here and there that will form black holes. Of course, the whole universe is not a black hole, obviously, otherwise we could not be here. Okay, so let's see something crazy happening if I use straight this definition. Okay, so let me suppose now I don't have any overdensity. I just have the Friedmann-Robertson-Walker universe. Okay, I just have that. So what happens now? So now let me calculate the Misner-Sharp mass. Misner-Sharp. This will be 4 pi integral from 0 to r rho bar. Now, what is the area radius of Friedmann-Robertson-Walker? Well, it's the term that multiplies the omega square, right? So in Friedmann-Robertson-Walker, it's simply r square scale factor square. right? This is Friedmann Walker is as simple as that. So that thing is just a to the cube r tilde square dr tilde. Okay, so this will be the Misne-Sharp mass, which is actually what we calculate. For example, is the same mass if you have done the exercise of Oppenheimer-Snyder collapse on dust. Okay, so this is actually the same mass you actually use, because this is, that dust goes like 1 over a to the cube, so this is a constant mass. Okay, but doesn't have to be like that, because the universe is not dominated by dust. And in fact, because we are talking about the universe before structure formation, we are actually talking about a radiation-dominated universe. Okay. Anyway, so this is not a constant. Okay. But then what we get is this, equal to 4 pi divided by 3 rho bar a to the cube r to the cube, right? I mean, this is very simple to integrate this thing. So you immediately see that because this doesn't cancel out, okay, so rho bar scales different than dust, okay, there will be some time for which, if I divide it by r now, if I calculate 2m divided by r, I can always find some time for which this is equal to 1, okay? So does that mean that the universe has, at a certain point, was a black hole? Obviously not, okay? What happens there? Well, there it happens that there is an horizon, but this horizon is the cosmological horizon, okay? So it's not forming a black hole. It's causally disconnecting matter from inside to outside, okay? But it's not a trapped horizon. So what happens here, differently from the case before, is that actually I don't have this asymptotically flatness.
I'm sorry, I missed that. So what
Okay.
do you say about the universe?
So what I'm saying is that there is always a time, okay? Or if you want a scalar, you can take it either a scale or a time. This is an equation such that 2m over r is equal to 1. Reason is that this guy changes in time. Okay? So I can always find a moment or a point in space, so a radius, such that this is an horizon. This is a trapped horizon. In fact, the trapped horizon, it exists in the universe, and is the cosmological horizon, precisely. Okay? But that's not a black hole. Okay? So there is something we have to do to use all this nice machinery that Thorne invented for asymptotically flatness, but in the case of asymptotically Friedmann-Robertson-Walker universe, so something that has an homogeneous component. And so our imagination, then it plays a role. And then what do we do? So if we have something that at infinity has not zero density, so what do? We simply subtract it. Okay, so at least we are simulating the idea of asymptotic flatness. Okay, so let me define then a new mass. Why I want to do that? Well, because as we just saw, if I just take the infinite wavelength perturbation, so basically the Friedmann-Robertson-Walker universe, this forms something that I'm not interested in. It forms an horizon that would not form a black hole. Okay? So let me remove that thing. Let me remove this thing. Okay? What I'm interested now is just something that has a gradient. So what do? Then let me reintroduce now what I call overdensity that we used before, okay? Which is something which is the energy density, a full over energy density we have, minus the background one. Okay? So I'm actually now calculating the what I call the overmass, Misne-Sharp, which is like before, but instead of using the full energy density, I'm subtracting from this energy density an infinitely long wavelength. Okay, the part that goes to infinity. Okay, so I'm making energy density 0 to infinity, basically, simulating that. So this is 4 pi, the integral of delta rho r square r prime dr. So still, let me assume that I have an overdensity that is spherically symmetric with respect to its value. Okay, so it's like a peak, a large peak of overdensity, and it's spherically symmetric around. We'll see why this is relevant. Okay, but for now, let's stick on this simplification. Okay. Okay, so then if we look at the metric, in this case, so I have a large overdensity, which is spherically symmetric, okay, on an asymptotically Friedmann-Robertson-Walker unions. Well, the metric looks like the following: dl square equal to r prime square dr square divided by 1 minus 2 m Misne-Sharp divided by r plus r dot square plus r square d omega square. So this is the special part. Now, funny enough, you can see that this is basically what you would call naively the full energy, because it's the potential energy plus the kinetic energy of your space-time. No? In a way, we can say. Okay? Because it's the time derivative square, so it's kind of the velocity. Okay? It's like the Hubble constant, if you want, is your kinetic energy of the unions. Okay. So, and this is precisely the Misne-Sharp mass that I have calculated before. Okay. Not the delta, the Misne-Sharp. Okay, so not the one minus the background. So I would put delta. Okay. And now you can see in this paper I was telling you before, how I worked. Okay. So you can see that actually this full generically, the Misne-Sharp mass, it's proportional to the integral of r square r prime. So this is coming from Einstein equation. Okay. So I put this metric into the Einstein equation. Okay. Now I'm using Einstein equation. Before I was using just my intuition of geometry. Okay. Now is Einstein equation. I find that the Misne-Sharp is equal to this. Okay, so the 0,0 component, where I'm using here the asymptotic time of the universe, which is the cosmic time. Okay, so this t, the 0,0 is the asymptotic time. Okay, you can see, by doing a little bit of massage of Einstein equation, you will find this. Okay, so so then we see immediately that again this is a scalar, because the as I said, in spherical symmetry, the area radius is a scalar. Okay, and the t.
I just had a couple of questions.
Yes.
So this line element is again inside this collapsing shell.
This is actually extending also outside. So this is from inside to outside. It's the full space-time.
All the way. Okay.
All the way, from 0 to infinity. The only thing that I'm assuming is that the whole system is spherically symmetric around a large peak of your overdensity.
And the space-time itself, the dt squared and the a.
Yeah, there will be some lapse. So some lapse here. Okay. So this is the time part.
And the scale factor?
The scale factor is included into this R. For example, in Friedmann-Robertson-Walker, R is R small, which is the coordinate here, multiplied by the scale factor. So generically is a function of time. Okay, so it might be separable, invariable, but this will be Friedmann-Robertson-Walker. So typically it's not. Okay, so more generically, it's just, I mean, this is as generic as I could be. Okay, so the only thing that I wrote it in a suggestive way to show that here there is a total energy somehow. And if you plug this metric into your Einstein equation, you find that actually this object that's sitting there is precisely what we were calling. No? Yeah. works. Okay. So, so you see that in this form, this is actually again well, is a scalar as we said before. Okay, so it's the full energy density multiplied by the area radius. So this mass, it's again a scalar. Okay, so it defines a physical mass. Now, then if this is a scalar, this is also a scalar. Why? Because what I'm doing, I'm subtracting a fictitious function of time, whatever it is, so this is done once forever, and then I'm multiplying by another scalar. R itself is a scalar. Okay? So this over mass is again physical. Okay? And now the Hooke conjecture would be, in this case, that 2 times delta m Misner-Sharp divided by R equal to 1 would form a black hole. Okay, so now we got rid of this problem of the cosmological horizon, and we pin down the horizon due only to the overdensity that has a gradient. So it's not homogeneous. Okay? So there will be still another horizon that is the one of cosmology, but now we are interested on an horizon, a trapped horizon, that would form a black hole. Okay? So I have an overdensity, and this would form a black hole. Okay? How are we going? Until what time is? 5. 5 to, this is, in your watch is 4. It's nice. No, it's 5. It's 5. See, wow, I didn't talk of anything in 1 minute. Okay, so far, is that all right? So it's very intuitive. Okay, so what I'm doing is I'm simply saying this. Okay, everything is inside an horizon. My object is inside an horizon, then it's gonna collapse. However, the biggest problem is that in an expanding universe, I have something that also extends to infinity, and I have to subtract that part. Okay, that's what I did. Okay, so you will probably see tomorrow that you will actually get something similar, although probably in the lecture of tomorrow it will be in asymptotically flat space. Yes, so most probably. Okay, so but doesn't matter. So the concept will be the same. Okay. Okay. So any question until now? Good, looks clear. Okay, so let me erase something, if you don't mind, and let's pause a moment. So now we understood the condition. If I have a spherically symmetric space-time, that is, even if it is time-dependent, I don't mind. I know, yes. Scalar function, yes. Yeah, I meant scalar function, yes. Yeah, sorry, not constant. Because, of course, if the universe evolves, then the radius of a sphere also evolves. I mean, imagine a balloon that is expanding, then its radius must evolve as well. Okay. Okay, so what we want to find for primordial black hole is the condition for which eventually this function, that now, yes, I can give a name, compaction function, to delta m Misner-Sharp divided by R, I call it compaction function. Compaction function. This was the name given by Shibata and Sasaki in 1999. Okay, so I want to find the condition for which this compaction function eventually reaches 1 and then form a black hole. So you have to imagine you are doing numerical relativity. You have to imagine that you come with your code, and you ask me, okay, what are the initial conditions I have to put in my code in such a way at some point this will collapse into a black hole. Okay? So that will be my job, okay? Giving you the initial condition. Then you put in your computer, you will simulate, and you will see whether you will form or not a black hole. Okay? So that's the idea. Although we will see that we will not need the numerical relativity. Okay? Well, we'll need it as a test, but we can do it everything analytical. Okay. So before going through the initial condition to form a black hole, let's discuss something related to primordial black holes. Okay, so because so far this was completely general. This is the condition to form a parent horizon. So we need to find some initial conditions such that we evolve there. Okay. Now the idea is the following. We have our universe. Okay. So what we want is that in the past, when the universe was permeated by radiation, here and there, some large inhomogeneity. We have heard yesterday, or today actually, we heard today that the perturbation of the CMB are extremely small. Okay, so they are like a factor of 10 to the minus 5, so almost a million. Okay, but in order to form a black hole, we actually need something larger, as we said. As we also say today, okay? Anyway, so, but when we form a black hole in radiation, what happens is that this black hole becomes, as we want it to be, like a particle that only interacts gravitationally. That's why we are interested in using those as dark matter, right? So if I only interact gravitationally, their energy density, let me call it rho dot, scales like dust, like particles. And now we know that the dust just scales like the volume, a to the cube. Okay, so a is the scale factor, so the density scales like 1 over the volume. Now, if I have a box, this gas will scale like the volume. However, radiation, it actually scales differently. Radiation scales like 1 over a to the 4. Okay? So if we make a ratio, then we have that rho black holes divided by rho radiation goes like the scale factor. Okay? So what we want is that at matter radiation equality, what we want is that roughly rho dot over rho radiation is of order 1. Right? Because what we want is that basically the full of matter, not the full because we have also baryons, but okay, is of order 1. We know that dark matter is of the same order of baryons, okay, of us. Okay, in fact, it should be around us. Okay, and then what we want is that at the matter radiation equality, this has to be order 1, whatever, 0 point something. Okay, but it's roughly order 1. So now we introduce today the number of e-foldings. Okay, so this scale factor, it's actually then we can rewrite in terms of the number of e-foldings back in the past. So what we have is that rho dot divided by rho radiation goes like e to the minus the number of e-foldings from now, so if we put 0 now, to back in the past when we form e to the plus. Okay, so you can see that even if I started with extremely small number of primordial black hole at formation, because this was a long time ago, today they are exponentially larger than before with respect to radiation. So what we can have a ridiculously small number of primordial black hole at formation. So basically the universe is still radiation dominated. Okay, but if we wait enough, then they will actually dominate the universe. Okay? That's the idea. Okay? So at formation, we actually need that primordial black holes, these black holes are very rare. Because otherwise they would be exponentially larger now. Okay? Okay. So, so this fits very well actually with what Sriram was saying today about cosmological perturbation. Why? Because what we say today is that cosmological perturbations are very small, okay? But this is a statistical concept. Okay, so what does it mean? It means that in average, they are extremely small fluctuations. However, as you can imagine, let's take, for example, a Gaussian statistics. Okay, so if I take a Gaussian statistics, and I take, so this is the Gaussian probability distribution, okay, of some variable, x, its average is 0. Okay, but of course, I can ask, okay, what is the chance to have value of x larger than certain value? This is not 0. Okay, so even if in average, so everything is populated by 0 fluctuations, okay, there is some chance, some exponentially small chance that I will actually have large fluctuation here and there. And this is what I want, because what we want is to form exponentially small number of primordial black hole. Okay? That's the relation with inflation now. Okay? Because inflation is telling us that the fluctuations are actually very small, statistically. Okay? But we have a statistical analysis that we can use. Okay, okay, so let's see a little bit, let's make a connection then with all this machinery that was quite generic for collapse of a black hole, and let's make a connection to inflation. Okay, the first thing we want to know. Is that clear what I'm saying? Right? So the fluctuations are statistically distributed, because this is a quantum system. A quantum system roughly is not true, don't tell Bell, but is roughly a statistical system. Okay, so in fact, what happens is that when perturbation goes over horizon, super horizon, as we heard today, they become classical. We say they classicalize. There is all this theory of the squeezing state and whatever, but basically they are classical state. So classical state doesn't mean that they are just one trajectory. No, it means that they are distributed statistically. Okay, and what we saw today as the power spectrum is simply the variance of this distribution. Okay, that's the variance. Okay, very good. Okay, so let me write down the most generic metric in what we call ADM formalism. Okay, ADM formalism is simply for Arnold, Desern, and Misner that invented a way of rewriting a generic metric. But okay, you can immediately see that this is completely generic. So if I write the metric dx square equal to minus alpha square dt square plus, what I'm making explicit now, I'm using the scale factor of Friedmann-Robertson-Walker because I'm thinking on perturbation over Friedmann-Robertson-Walker. So I'm extracting explicitly this factor, okay? And then here I write it as e to the 2 zeta, gamma tilde ij, and dxi plus beta I dt, and then the same with j. I haven't done anything. This is really completely generic. Okay, the only thing that I have extracted the scale factor here, so a Friedmann-Robertson-Walker will be zeta equal to 0, gamma tilde equal to delta ij, beta equal to 0, and alpha equal to 1. Okay, otherwise it's completely generic, right? What I'm using here in this form of the metric is that the determinant of gamma tilde ij is equal to 1. This is a matrix, okay, so I can choose gauges such that this is equal to 1, okay? This is completely generic, it's not perturbation It's not perturbation theory. Okay? It's really full GR. Now, the point is the following, that the inflation, as we heard today, is generated by a scalar field. Okay? So what we are mainly interested in are scalar perturbation, because they are sourced by a large scalar field. So the gravitational wave, we heard today that they are also formed, but they are going to be smaller than the scalar perturbations. Okay? So the scalar perturbation are our king now. Okay? So we are considering those. Now, if we are considering those scalar perturbations, what we also heard today is that we can actually decompose our perturbation in sub-horizon and super-horizon modes. Okay, so this is in perturbation theory, but in full general relativity, this is what is called gradient expansion. What does it mean, gradient expansion of general relativity? It means that I take all the gradients of my Einstein equation, and I take the leading order of these gradients. So that means I'm taking only in consideration perturbation that have a wavelength very large, larger than the horizon. Okay. So if we do that, if we consider only super horizon scale, this is all beautiful mathematics in general relativity, which is called gradient expansion, but I'm not gonna do it all here because otherwise it will take 1 week course. Okay, but bear with me. So this is, I can do at super horizon, I can do the gradient expansion. So you can see immediately the following. Now beta, let's see before beta, okay? Beta I. So this is a vector, right? It has an index, so it's a vector. But I'm thinking only to scalar perturbation, correct? So this must be a derivative, a gradient of some scalar, right? So the first thing that we do, we neglect this. Why? Because this is a gradient, so we are doing gradient expansion, and so we completely neglect this part. Okay? So the first thing that we forget is what we call shift. Okay? So this guy is called shift. Okay? These are super horizon scales.
But now we are assuming that they are perturbated.
No. This is gradient expansion, it's not perturbation theory. So this is, I insist on that because, in fact, to form a black hole, you have to be far away from perturbation theory. Okay? The only thing that we are considering is that we are taking wavelengths that are very large, or whatever large perturbation you have, but those are super horizon.
But if it is not linear,
yeah,
can it still Fourier decompose them?
You can, of course.
You can Fourier decompose.
Yes. I mean, that's not a problem. Any function is. Okay. So the first thing that we are going to neglect is this. Second thing that we are going to neglect, well, you can already imagine that this gamma tilde ij, it's a tensor. Okay? Because we are not caring about gravitational waves. They are super cool and super interesting, but not for this problem. Okay? Then you can understand that delta ij, I can rewrite in terms of, gamma ij is delta ij plus, let me call it delta gamma ij. And this guy is what is related to gravitational waves. Okay? Because this is, in fact, you can define with the determinant equal to 1, and you can see that this part has to be transverse traceless, for example, in perturbation theory, and so far so on. So we are also neglecting this because we don't care at the moment on gravitational waves. So this I'm talking about super horizon scale. So this guy, it's basically a delta function, Kronecker delta function. Okay, so you see we are simplifying a lot our metric, even if it's completely non-perturbative. Now, this is a scalar field theory. Okay, so a scalar field theory has a clock, which is a scalar field, So I can measure actually my time by looking at the scalar field. Okay, or at the scalar mode, whatever mode we call scalar mode. Okay, so because now we are left only with this variable zeta. Okay, this is actually related. One can check it's related to the Hamiltonian constraint, so it doesn't evolve. So the only degrees of freedom that is evolving is zeta. So this is actually our clock you can think of. So roughly speaking, you can imagine that then this alpha square must be something like 1 plus whatever zeta dot dt. Sorry, this should be alpha. Why? Because I mean, if I take some dx equal to 0, because for each dx equal to 0, then I can make a new clock related to the zeta. Okay. Now you have seen at least from perturbation theory, that during radiation, which is what we are interested in, this zeta dot is roughly 0. Zeta is constant. Okay. And in fact, you can prove that this is not only valid in perturbation theory, but also non-perturbatively. So after all, this very complicated metric, it's actually simplified at superhorizon scales in the following form. ds square. When I say this, I mean superhorizon scales and approximately a leading order in the time derivative as well. T square plus e to the 2 zeta delta ij dxi dxj. I need the scale factor. Yes. I already did. Yes. Okay. So you can see what this guy is doing. So it's basically for each patch, is changing our scale factor roughly. So this is what he's doing. This is what is also called the local universe approximation. So that means that I can have whatever space-time I want. If I look at very large scale locally, it will always look like a Friedmann-Roberts-Walker space-time. It's just that one patch will evolve with one scale factor, another patch will evolve with another scale factor. I think we had a question yesterday on this, right? So this is in full glory what is happening. Okay, or is related what is called delta M formalism, whatever. Okay.
Can I ask a couple?
Sure.
So one, you mentioned a remark about single clock scalar field.
Yeah, it's a single scalar field.
Now, is this true only during inflation, or it's true post-inflation as well?
As long as you only have one scalar degrees of freedom.
But the question is the scalar field have to evolve monotonically?
Well, okay.
So it's
So
oscillating back and forth. It may have multiple values, multiple times corresponding to a single value.
right. Right. So I'm thinking, yeah, that's correct. I'm not thinking about reheating, for example.
Okay.
Yes. So it has to, I mean, it has to be possible to invert time with the scalar. So you have to have a trajectory that of course, yeah, that's important. Yeah.
Rosenberg has made some proposals where you can have this periodic clocks that effectively provide monotonicity to the
Sure. Exactly. Yes. Correct. You can always find yes a gauge in which it is possible.
There was another question I had. You mentioned that zeta dot is 0 even non-perturbative on super horizon, super scales.
How do I prove that?
Can you,
Well, this you have to use the Einstein equation. So you have to use the Einstein equation, and you have to. So you have to use the Einstein equation and use gradient expansion. So do the expansion into gradients, and you will see that basically this zeta dot, unless you use a funny gauge, this zeta dot it's roughly constant. Which follows. Sorry, zeta is roughly constant, so zeta dot it's 0, unless unless you are at least in an inflationary background, and so in an adiabatic evolution. Okay, so which is slow roll, for example, or it is radiation. So those are all adiabatic. So you can imagine that when something is adiabatic, so it evolves very slowly, Okay, so that means that if you have a wavelength that is very large, even if it is not perturbative, if it is larger than your cosmological horizon, it's causally disconnected, so it cannot evolve.
But in periods like ultra slow roll, I know.
But this is not adiabatic. Yes, as you say today. That's the point. So you have to be in adiabatic. So this is all in radiation. As you said today, which is correct, what we are interested in is from the end of inflation that we take the power spectrum onwards. Okay, so how we will get the initial condition to the end of inflation is a matter of what you explained today. That's why I start from there. Right. So this is really, we are in radiation. Okay. Okay, so so now we have simplified at super horizon scale this object, okay, and we'll see why I'm talking about super horizon scale, because you can imagine now if you start to connecting what I said before, you can say, well, but at super horizon scale, I'm not going to form a black hole, right? So I need to go inside the black hole, inside the horizon, otherwise I will not form the black hole. Correct. But what we are gonna do, that's the interesting thing, is give the initial condition of your numerical code at super horizon scales. Because everything is simpler there. Okay? As we can see, I mean, everything reduced to to few equations somehow. Now, what we are gonna do, which is what we have done today, is to Fourier expand this zeta. We can still do it. This is fully nonlinear. Doesn't matter, we can Fourier expand, okay? We know that this zeta is asymptotically 0, because it's asymptotically it's Friedmann-Robertson-Walker background, so it can be Fourier transformed, okay? So then I define zeta equal to 1 over 2 pi to the cube, the integral of zeta k e to the I k x d3k. Okay, so this is the Fourier decomposition of this function here that depends on x. Okay. So now it comes our assumption that we'll do in this course. Okay. So this zeta, as we saw it today, is related to the Bardeen potential that we are discussing today. Okay. In fact, in this form, this zeta is actually R. Okay, so what we saw it today, it's this guy is that. Okay? In fact, as we comment today, we should have put a K. Okay, so the curvature perturbation is this zeta. Okay, you can check. And so, as we discussed today, this is obtained quantum mechanically, okay, by quantization of our scalar field, right? And so that means that this is, once this goes super horizon scale and become a classical object, it is distributed statistically. What we check in the CMB, we do the volume average of all possible over temperatures. Okay, so what we do when we calculate the CMB is basically to relate everything to the 2-point correlation function of zeta, which we define the following way. So zeta k prime. So for the CMB, this is fine. Okay, so I can calculate this, and I'm happy with that. Why? Well, d3 k minus k prime. This is due to the isotropy of space-time due to the scalar field, divided by k to the cube, and I have the power spectrum of curvature perturbation. Okay, so we saw it this today. Okay, now for the CMB, this is calculated perturbatively as we saw it today. Okay, so and we are perfectly fine with that, because what we check in the universe is that the universe, the temperature fluctuation so far looks like distributed Gaussianly. Okay. And you know better than me that if I take a quantum field that doesn't have any interaction, its distribution is Gaussian. Okay? So that means that if it doesn't have any interaction, linear theory is the same as full perturbation. Modulo, there is some gravity stuff, but okay. So for the CMB, this is correct, and so far observationally we haven't seen any non-Gaussianities. That doesn't mean that there are no non-Gaussianities. Okay, but as a working assumption now, we are going to use for this course that zeta is Gaussian, fully non-perturbatively. Okay, so we are a step forward than the data. Now, if zeta is Gaussian, a Gaussian distribution, probability distribution, is determined just by its variance. Okay, so once I give you the variance, I have the full probability distribution, right? Okay. And yes, so basically what we are assuming is that the probability distribution of zeta k of each Fourier mode is actually Gaussian, right? And its variance is, well, the normalized variance is the power spectrum. Normalized because I normalized by k to the cube. This is called dimensionless power spectrum, because otherwise we'll have volume for the delta. No? We'll have volume dimensions. Okay, so then what we are interested in, we are not interested in this part of the probability distribution, because this part of the probability distribution, as we saw it today, is the CMB. What we are interested in is very rare event, exponentially small events, okay? And so those are the tail of this distribution. So what we are going to explore now is how to relate this exponentially rare event with the initial condition to form a black hole. Okay, so that's what we are going to do. I think I'll stop here. I think this is a good point to stop. And tomorrow, we will basically connect to the compaction function. We'll connect the perturbation to the compaction function. And once we do this connection, we can actually start thinking about the statistics of the compaction function. Okay, thank you for listening.